Hi there, everyone. Welcome back to Christianomics. My name is Krish Vijay, and today I'll be talking about stationarity. Now, in my previous video, I mentioned that I will talk about ARDL. However, I realized that before we could talk about ARDL, I should first cover the topic of stationarity in order for you to understand some of the prerequisite of ARDL. Now, in many econometric analysis, we often use time series data. So what time series data are is technically data where we have observations that are collected over a certain period of time. So we don't just have one data at one particular time. It's we have data of that particular variable over many different time period. So some good examples are, for example, GDP. For GDP, we have yearly figures. So we have like, okay, what's the GDP for 2009, 2010, 2011? And if we collect all this data from say 2009 up to 2020, so then this become a time series data. Similarly, we have also inflation rate, which we could collect at a monthly frequency, and stock prices on a daily frequency. In fact, you can even argue that stock prices can be collected on a by the seconds, right? So another thing concept that I should probably write here is frequency. So frequency means how often you collect the data. So daily, monthly, quarterly, yearly. Now, um, so here's why when dealing with time series data, the concept of stationarity is very important. And this is because stationarity determines whether the statistical properties of the particular time series would actually remain stable over time. And these statistical properties I'll explain in the following slide. Now, another reason why this stationarity is very important is because in econometrics, there's a most methods actually tend to require stationarity to be present in order for the results to be valid. In other words, let's say your time series data is not stationary. In that case, whatever results you get tends to be invalid. So you have to be very careful about this. Now, a time series is stationary if its statistical properties do not change over time. And what these statistical properties are is the following. Its mean should be constant, its variance should be constant, and lastly, its autocovariance should also be constant. Now, if you look at this, it says your covariance between yt and yt minus k depends only on the lag k, not on time t. Uh, Now, it looks a bit confusing, but it's not that difficult. I'll explain it to you. So let's assume we have a data where, let's say it's on a daily frequency. So I write here daily. Okay. A daily frequency of, say, number of sales. Say your number of sales. Let's say coffee. And let's say we're talking about, say, January. So in January, you have, say, day 1 until to the 31st, right? So let's say for each day, day 1, day 2, day 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so forth. So this will be the day. And we have sales. So let's say you have a value on day 1. We call this, say, D1. For example, the sales on day 2 is D2, D3, D4, and you get it, right? So what autocovariance means is the covariance between within the series, right? So let's say we are taking, say, what's the covariance of, say, day 1 and day 2, right? So if the covariance should be constant, so we will have something like this. Covariance of say 8 and 9, D8 and D9. So in other words, let's say we take covariance between day 1 and day 2, it should be the same as covariance between day 8 and day 9, right? And if we take say covariance between day 1 and day 3, so there's a separation of two legs here, right? So then this become covariance D1 and D3, D8 and say D10, right? So this should also be the same. It shouldn't be the case that the covariance D1 and D3, uh, if you take it on a different time period, let's say where you have a difference between two legs, suddenly the covariance is different, right? So that's what it means that it depends only on the leg K. Meaning say how far apart this is your K. Your K here is 2, right? It's not on the time. Meaning say at any point, if I were to simply just randomly take this 5 and 7, it will still be the same. So that's what the constant autocovariance is here. Now, if you talk about stationarity, visually, if you are just trying to eyeball it, this is how on the left, how a stationary time series variable will look like. So essentially, when you look at it, you can sort of like take a guess that okay, it's starting from here, it's going down, up, down, but okay, it's fluctuating around some kind of value, right? I could take a guess that maybe it's going around 0, or maybe somewhere between 0.5 and 0, maybe 0.1. But what this means is that just one look at it, you could roughly forecast or take a guess that, you know, in the long run, the value will be around, say, 0 or say 0.2 perhaps, right? I could even take a guess that, after this, it might just go up here, right? So this is how uh, a stationary time series data is. But with non-stationary, it's a bit more difficult to predict what's the mean value, right, over a long period of time, right? Because it's keep increasing here. You can see it's like trending upwards, right, in the long run. So this on the right hand side is what we call non-stationary. Now, so earlier we talked about why stationarity matters, right? Why it's important for us to care about stationarity. But we should now talk about it more in depth. Okay, the problem is that when you have a non-stationary time series, sometimes we call it as having unit roots. All right, another way to call it non-stationary is that we will have incorrect statistical inference. So this can happen, especially our least square estimators um, tend to be, how should I put it, a bit biased downwards. And this is especially in the case when we have small samples. Our test statistics also become incorrect in the sense that t-stats usually follows in normal distribution, but when your time series is non-stationary, it's no longer a normally distributed sample. So t-statistic becomes you cannot follow it anymore. And also our predictors also tend to become unreliable. The second one is there's actually no mean reversion, or what we call infinite memory of persistence. So remember earlier the um I can't go back. Okay. But what it means is that in mean reversion, it means that even if there's a shock to the variable, let's say like there's a financial crisis or something, right? There's a shock. But in the long run, it will still go back to its mean, right? Therefore, your mean will be always constant over a long period of time. But if it's non-stationary, once there's a shock to the system, the shock will remain, it won't go away, and you will just continue. Hence, infinite memory or persistence. Now, the third one is the most important, the spurious regression part. So when you have a non-stationary time series data, you tend to have spurious regression if you were to use two different time series data and you were to regress it. Some of the hallmark of a spurious regression is that your results tend to have high R square and significant T stats, right? So when you look at this, you might think, okay, it makes sense. Maybe it's high R square and significant T stats. So, there's a relationship. But in reality, that isn't the case. So here's an example, right? Okay, so spurious regression means two or more non-stationary time series that looks related but aren't. So I took some data from the World Bank Development Indicator. So here's two different time series data. On the left, I have broadband subscription for per 100 people in Japan. So for every 100 people, how many people have broadband subscription in Japan? And as you can see, this time series data I took from 1998 to 2023. You can also download it later and check. So it's trending upwards, right? Okay, good. Now, the total population in US is also trending upwards. Fine. Now, logically, if you look at these two, and I have to ask you, is there any relationship between these two? You would say probably not, right? But let's say we didn't think about it that far, and we were just to take this two time series data and we want to do a regression. Okay. So let's regress total population of US on broadband subscription of Japan. And so this will be the broadband subscription and this will be the total population, right? So here's what I got. Okay. So our beta 1 here for the broadband subscription, you got a coefficient here, right? All right. Don't really care about that so much. But look at the T stat here. It's 19.33, which is really high, right? And another thing, look at R square. We have 0.9397, which is above 0.9. Okay, so this thing. We got R square of more than 0.9 and also highly significant T statistic. So if we just to use that, we would think that okay, the model suggests that if broadband subscriptions for every 100% in Japan were to increase, total population in US will increase. Meaning say that the more number of people subscribe to broadband in Japan, then the total population in US will increase. If you were to really think about it, this doesn't make sense. Yet, we have high R square and significant T stat. The reason is because when you take two variables that are, having same trends going upward, and you have to regress one on the other, the calculation would make it look like as though these two are actually related, right? And so what you call spurious regression is also sometimes known as nonsense regression. Yep, I should have mentioned that. Okay. Now, for the types of stationarity, there is usually two types of stationarity. The strict stationarity is quite a rare case. So usually we don't require strict stationarity because it requires that the entire probability distribution remains constant over time. So meaning say that at any point in time you take it, you should expect that the probability distribution is always constant, right? But that just doesn't, that's always way too rare. So we don't require strict stationarity. Instead, most econometric methods only require weak stationarity or what we call covariance stationarity. So it means that your mean, variance, and autocovariance should be constant. And as long as you have these three statistical properties that are constant, then you can say that our time series data is stationary. Now, another concept that is very important in stationarity is the concept of order of integration. Now, a series is integrated of order d if it must be difference exactly d times to become weakly stationary. So, uh, one of the things that we do in time series is that sometimes if our data is non-stationary, we will difference the data in order to make it become stationary, right? I'll give you an example. Let's start with the the basic one. If you have an I0 is what we call as stationary or integrated of order 0. So I0 means your time series is already stationary, right? So you don't have to do anything. It's already stationary in its level form. Just remember this, right? We will talk about this next time in ARDL perhaps. So since it's already stationary, we don't have to do any differencing, right? Now, if you have I1 or integrator of order 1, right? Now, it means that this time series is not stationary. So we should uh, at least difference it once, right? So it becomes stationary after first difference. So what we do is we take the data, we minus by its previous um, one time period before value. So we get its first difference. So one of the things with this is what it also means is that if initially for YT, your observation number is 31, so if you do first difference, right? So now your observation value actually drops to 30. So you have to just take note of this. Now, similarly, if it's I2, integrator of order 2, it means that you need to difference this particular series twice before it becomes stationary, right? No differencing. Okay, I'm not so sure what is this, but yeah, it's probably wrong. So we can just forget this. But technically, if it's I2, you need to differentiate twice in order for it to achieve stationarity. Now, side note, not all variable actually needs to be different to achieve stationarity. There's some cases where the series is, they have a sort of deterministic trend. So if we just add a trend variable into it, then we can detrend it, sort of, and then it becomes stationary. But we're not going to cover this today. Now, to test for stationarity, just now initially we tried to eyeball it and just look at it, the series, and said, oh, maybe this is stationary, maybe this is not. But in time series or econometrics, we need to have formal tests sometimes, right? We cannot just say, no, let's just eyeball and look at it and say whether it's stationary or not. And so there are several statistical tests that we have to determine a series is stationary. So some of the common one is augmented Dickey-Fuller test, ADF. So the null hypothesis is stationary. The H1 is unit root. So if by running the ADF test, if we have a highly significant t-stat, then we can say that, okay, we can reject the null hypothesis. And so there is actually a unit root, meaning that it's non-stationary. Now, even Phillips Perron, the PP, this test here has the same hypothesis as the ADF, right? But just take note, for the KPSS, there's another test called KPSS. Now, if you to run this test, just remember that the hypothesis is reversed. Means say that this H naught here means unit root, and this H1 means no unit root. So in other words, stationary. This will be not stationary, right? Okay, so I think that's all for today. Um, yeah. So thank you so much for listening to my rambling. I hope that you can understand what stationarity means, and then with that we can in the future talk about ARDL, and you can understand why ARDL bound testing approach is very useful. Right. Thank you for listening, and if you like this video, just hit the like button and also subscribe to my channel. Right. I'll see you next time. Bye.